Somewhere about 1,300 light-years from Earth, a star swallowed one of its own planets. The whole event, on cosmic timescales, was over in days. The planet is gone. There is nothing left to see, no debris field, no visible scar on the star's surface, no signal anyone could have detected in the moment it happened. On the night it occurred, every telescope on Earth was pointed at something else, and not a single instrument recorded the event directly. What happened in that system is, in a strict sense, gone forever. And yet, last week, a team of researchers from the University of Michigan published a paper in the Astrophysical Journal saying they know it happened anyway. Not because they saw it, because they read the star's chemistry, and the star gave itself away. By the end of this video, you will understand what they found, how a single element became the fingerprint for a destroyed world, why this particular star should not have been able to eat a planet at all, who the accomplice was, and what it means for the planet you are standing on right now. Let's get into it. The star is catalogued as TOI 5882. It sits about 1,300 light-years away, in a direction that carries no special significance and no name most people would recognize. From a distance, it looks unremarkable. It is slightly larger than our Sun, roughly twice the diameter, and it is at a stage of life astronomers call the subgiant phase. A subgiant is a star that has burned through most of the hydrogen fuel in its core and begun a slow transition toward its next chapter. The core has contracted, the outer layers have started to expand, and the star's interior is rearranging itself on a timescale of millions of years. It is not a dramatic phase. Nothing about the subgiant stage looks alarming from the outside. TOI 5882 appeared to be an ordinary star moving quietly through a predictable and well-documented stage of stellar evolution. That appearance was wrong. The clue was hiding in something so small that you could easily overlook it: a single element, lithium. Lithium is the third element on the periodic table, one of the lightest substances in the universe, produced in the first minutes after the Big Bang and later forged in certain stellar processes. Stars have some lithium, planets have a great deal more. The reason for that difference comes down to temperature. The interior of a star is hot enough to destroy lithium. As a star ages, the outer layers where lithium lives get deeper and hotter, and the lithium that was originally there gets mixed down into regions where nuclear reactions break it apart. The older the star, the less lithium it should have at the surface. By the subgiant stage, a star has been burning for long enough that its surface lithium should be significantly depleted. This is not a theory, it is a well-observed pattern across thousands of stars, consistent enough to be used as a measuring tool for stellar age in interior structure. TOI 5882 had too much lithium, not slightly elevated, not borderline. The team compared the star against 62 other subgiant stars at a similar evolutionary stage, matched for size, mass, temperature, and age. They built as controlled a comparison as stellar astronomy allows, and TOI 5882 ranked in the 98th percentile for lithium enrichment. Only 1 or 2 stars out of every 100 at this stage of life carry this much lithium. For a subgiant to have surface lithium this high, something must have delivered it from outside. And there is one very efficient way to deliver a large amount of lithium to a star from outside. You feed it a planet. Brooke Cotton, the graduate student at Michigan who led the study, described the reasoning directly. Planets are heavily enriched in lithium relative to stars. If a star consumes a planet, the planetary material gets mixed into the star's outer layers, and the lithium comes with it. You are what you eat. The lithium in TOI 5882's atmosphere is not there because the star produced it or retained it unusually well. It is there because the star absorbed the world, and the world's chemistry is now part of the star. Astronomers call this process engulfment. The word is accurate but understated. What it describes is the complete destruction of a planetary body by stellar gravity and heat, a world that may have existed for hundreds of millions or even billions of years, with its own orbit, its own geological history, its own chemical composition, absorbed into a star in a period of days to weeks and incorporated permanently into the stellar atmosphere. On human timescales, days to weeks sounds like a prolonged event. On the timescale of a planet's existence, it is instantaneous. One moment the planet is there, then it is not. And the only record it leaves behind is the faint chemical signature it deposits in the layers of gas it passed through on the way in. That signature is what Cotton's team found, and finding it required the kind of careful, multi-step analysis that is worth understanding because it is the reason the claim is convincing rather than speculative. The team used a technique called spectroscopy, which works by splitting starlight into its component wavelengths and measuring how strongly different elements absorb or emit at specific frequencies. Every element has a unique spectral fingerprint, a set of wavelengths where it interacts with light in a distinctive way. Lithium has its own fingerprint, and the strength of that fingerprint in a star spectrum tells you how much lithium is present at the surface. The measurement for TOI 5882 was not ambiguous. The lithium signal was strong, and it was strong in a way that placed the star sharply outside the normal range for its evolutionary stage. The researchers also had to rule out the alternative explanations for elevated lithium, things like unusual stellar interior processes or membership in a special category of lithium-rich stars that exist for unrelated reasons. They worked through those alternatives systematically, and the picture that remained at the end of the analysis was a star that had recently gained lithium from an external source. The most consistent explanation for that external source was a planet. Now here is where the story gets stranger, because there is a problem with the simplest version of this explanation. When astronomers think about stars swallowing planets, they usually picture the end game of stellar evolution. A star reaches the end of its fuel supply, its core collapses, its outer layers expand enormously, and as the star grows into what is called the red giant, it physically overtakes the orbits of nearby planets and absorbs them. This happens on a predictable schedule, and for stars like our Sun, it happens billions of years in the future. It is the expected, almost routine finale of planetary systems around aging stars. TOI 5882 is not a red giant. That is the problem. It is a subgiant, an early transitional phase, and at the subgiant stage, the star has not expanded enough for its outer boundary to reach any planet in a normal orbit. The expansion explanation does not work here. The star did not grow into the planet. Something else pushed the planet in. And that something else is where the second major character in this story enters. Also orbiting TOI 5882 is an object called TOI 5882b. This companion is not a planet and not quite a star. It is a brown dwarf, a category of object that exists in the space between the two. Brown dwarfs form the same way stars do, from a collapsing cloud of gas, but they never accumulate enough mass to ignite the sustained hydrogen fusion that defines a true star. They are too large to be planets and too small to be stars, a class of failed ignition that sits in permanent astronomical limbo. The brown dwarf companion to TOI 5882 is about 20 times the mass of Jupiter, which places it comfortably in the brown dwarf range. And it orbits the star every 7.1 days, which is a tight orbit, close enough that its gravitational influence on anything else in the system would be significant and persistent. A companion this massive, orbiting this close, is not a passive bystander in the planetary system. Every orbit it completes, it exerts a gravitational tug on every other body in the system. For a planet in the right orbital configuration, that tug is not random. It accumulates in a preferred direction, gradually deforming the planet's orbit in a way that compounds over millions of years. Think of it as slow-motion chaos. Each individual perturbation is tiny. Across a billion orbits, the accumulated effect can be enormous, shifting an orbit from circular to elliptical, then from elliptical to highly eccentric, and then eventually into a path whose closest point to the star dips inside the stellar atmosphere itself. At that point, the planet is no longer orbiting, it is falling. The working theory, which the research team is currently treating as the most likely explanation, is that TOI 5882b drove exactly this kind of orbital decay in one of its planetary companions. The process is called gravitational perturbation, and it is a standard mechanism in planetary dynamics, well documented in computer simulations and observed in various forms across dozens of planetary systems. It operates quietly on long timescales. A planet can spend hundreds of millions of years on a perfectly stable orbit, then find that orbit has been nudged into a configuration that carries it toward the star, then spend millions more years spiraling inward on a tightening path that ends in engulfment. The brown dwarf does not violently throw the planet into the star. It slowly opens a door that eventually leads there, and then closes it behind the planet permanently. This mechanism also explains the timing problem. TOI 5882 is not old enough for normal red giant expansion to have swallowed anything, but a brown dwarf companion driving a planet onto a destabilized orbit can operate at any point in a star's life, regardless of whether the star has expanded. The planet did not need the star to come to it. The star had help pushing the planet inward. And the lithium spike in the stellar atmosphere is the aftermath of that process, the chemical record of a world that will slowly walk to its own destruction over millions of years and then absorbed in a matter of days. Here is the part that connects this star, 1,300 light-years away, to the system you live in. The question of whether our own solar system has a history of planetary engulfment is not a hypothetical. It is an active area of research, and the evidence for it is more substantial than most people realize. The modern solar system has 8 planets, but the models that best explain the current arrangement of those planets, their orbital spacing, their resonance relationships, the structure of the asteroid belt, the behavior of the outer planets, consistently point toward an early history in which more planetary bodies existed than exist today. The leading model for the outer solar system's evolution, known as the NICE model, proposes that the early solar system contained an additional ice giant planet, a world roughly the size of Uranus or Neptune, that was gravitationally ejected from the solar system during a period of instability when Jupiter, Saturn, Uranus, and Neptune were reshaping their orbits. Some versions of this model can eject the extra planet outward into interstellar space. Others send it inward, toward the Sun. Whether the Sun ever actually consumed a planetary body in its history is an open question, but it is an open question that serious planetary scientists are actively investigating, not a fringe idea. There is also what is called the Grand Tack hypothesis, which proposes that Jupiter once migrated significantly inward from its formation zone, carving through the inner solar system before being pulled back outward by Saturn. If Jupiter did migrate inward in the early solar system, anything that was in its path would have been scattered. Some objects would have been flung outward into the outer solar system, some would have been pushed into unstable orbits that brought them closer to the Sun, and some, depending on the exact geometry, may have ended up falling into the Sun entirely. Jupiter at its current size is roughly 1,000 times the mass of Earth. A Jupiter mass object migrating inward through a young planetary system creates gravitational chaos on a scale that makes the TOI 5882 brown dwarf scenario look mild. If the Grand Tack happened, the inner solar system in its first 100 million years looked nothing like what we see today, and the Sun may have consumed planetary material in the process. There is also a chemical angle to this question, one that echoes the exact method used on TOI 5882. If the Sun consumed a planet early in its history, some fraction of that planet's material would have been mixed into the Sun's outer layers. The problem is that the Sun is old, roughly 4.6 billion years, and its outer layers have had far more time to mix and dilute any deposited material than TOI 5882's atmosphere has had. The subgiant stage, which TOI 5882 is currently in, is actually a favorable window for detecting engulfment signatures because the outer convective layer is relatively shallow. A thin layer of atmosphere holds the lithium signal without diluting it too quickly. In an older, well-mixed star, the same signal might be completely invisible by now, even if the engulfment happened. Which means that the Sun, even if it did consume something in its first billion years, has had plenty of time to erase the evidence. That is a genuinely uncomfortable statement, and it deserves to be held as one. It is not a claim that the Sun consumed the planet. It is a statement about the limits of what we can detect from inside the very system we are trying to understand. The forensic method that worked at TOI 5882, finding the lithium fingerprint in a star's outer atmosphere, may be completely unavailable to us when we try to ask the same question about our own star, because our star is old enough to have mixed the record away. Beyond the Sun itself, the question of what happened to the inner solar system's early planetary material bears directly on the history of Earth. The inner solar system, in the first 100 million years of its existence, was populated by more planetary embryos than exist today. The 4 rocky planets that survive are thought to be the products of a series of major collisions among a larger population of early worlds. Some of those worlds were absorbed into the surviving planets, some were ejected entirely, and according to some models, some of them ended up falling into the Sun. The fate of the planetary material that did not survive to become Mercury, Venus, Earth, or Mars is one of the open questions of planetary science, and planetary engulfment by the early Sun is one of the possible answers that no model has yet ruled out. There is one more thing worth sitting with in the TOI 5882 result, and it has to do with the planet itself, the one that no longer exists. The researchers estimated the mass of the engulfed planet from the amount of lithium deposited in the stellar atmosphere. The more massive the planet, the more lithium it carries, and the stronger the signal. Their estimate puts the missing world somewhere between a few Earth masses and roughly the mass of Neptune. That is a wide range, but it is a meaningful one because it tells you what class of planet this was. It was not a gas giant. It was not a Jupiter mass colossus. It was something in the range of a super-Earth to a sub-Neptune, a class of planet that turns out to be the most common type of planet in the galaxy by almost every survey ever conducted. Super-Earths and sub-Neptunes orbit the majority of Sun-like stars. They are the statistically typical planet in the universe. They are also, notably, absent from our solar system. Earth is the largest rocky planet here, and Neptune sits at the low end of the ice giant range. The gap between them, the super-Earth to sub-Neptune size range, is empty in our system, and planetary scientists have been trying to explain that absence for years. One hypothesis is that planets in this size range formed in the early solar system and were lost, either ejected by Jupiter's migration through the inner system or consumed by the Sun during the chaotic early period. If that is correct, then TOI 5882 may have just given us a close-up view of a process that our own system went through. A super-Earth or sub-Neptune falling inward under the influence of a massive companion, absorbed by its star, leaving nothing but a chemical signature that would fade over billions of years. The planet that fell into TOI 5882 is gone in every physical sense. There is no orbit to trace, no surface to image, no atmosphere to analyze. The only thing it left behind was a slight elevation in the lithium content of the gas wrapped around a star 1,300 light-years away. That signal will not last forever either. As TOI 5882 continues evolving, its outer layers will deepen and convect, and the deposited lithium will eventually be mixed inward and destroyed. The window in which the signal is readable is already closing on a timescale of millions of years. The team that found it did so during a brief period in the star's life when the evidence was still accessible. A few million years from now, the signature will be gone, and the engulfment will have left no remaining trace anywhere that any future instrument could detect. That is the larger story underneath the forensic result. Planet engulfment erases itself. It destroys the planet and then slowly destroys the record of the planet's destruction. The reason astronomers know this process happens at all is that they can sometimes catch the evidence during the brief window when it is still there. The reason they cannot fully quantify how often it happens is that for every case they catch, there are almost certainly many more cases where the signal is already gone or where the star is not in the right evolutionary stage to preserve it. TOI 5882 is a case they caught in time. The total number of planetary systems that have experienced engulfment is almost certainly far larger than the number of confirmed cases that exist in any database. What the Michigan team's paper does, beyond confirming this one event, is demonstrate how the forensic method works at a level of rigor that makes future studies credible. The control sample of 62 matched stars, the spectroscopic precision, the systematic elimination of alternative explanations, these are not the tools of a speculative claim. They are the tools of a detection that will hold up and that other teams can replicate on other stars. As survey telescopes produce larger and larger catalogs of stellar spectra, the same search can be run automatically on thousands of subgiant stars, looking for the same lithium anomaly, building a statistical picture of how common engulfment actually is and under what conditions it tends to occur. This paper is one data point. The method it validated could eventually produce hundreds. The planet is gone. The star continues. And somewhere in its outer atmosphere, mixed into the gas of a body a million times its mass, is what remains of a world that no longer has a name. A world that we may never be able to describe in any more detail than a size estimate and a chemical fingerprint. That is both the limit of what science can recover from a process this complete and the remarkable fact that it can recover anything at all. We will be tracking this story as the research continues. If this video reached you, please hit the like button. It helps more than most people realize. And subscribe if you want to follow where the science goes next. Drop a comment below and tell us whether you think our own solar system lost a planet the same way. We will be reading them.